Hello, my name is Jonathan Friedman. I'm former senior research associate at the Arecibo Observatory. Currently, I direct the Puerto Rico Photonics Institute at the Universidad Ana Jiménez. And this is a talk that I've given every year to the summer REU students at the Arecibo Observatory called the Mesospheric Refrigerator, Atmospheric Circulation and Thermal Structure, how atmospheric gravity waves couple to the mean circulation to produce the coldest place on planet Earth. And this is a highly non-intuitive uh, uh, phenomenon where the coldest place on Earth you would think would be in the winter polar region. And it turns out that quite the opposite is true. It's actually in the summer polar region under 24 hours of daylight. Just happens to occur at the top of the mesosphere at around 85 kilometers. And the purpose of this talk is to give an explanation of how that occurs. This talk was prepared with an awful lot of help, in particular thanks to Professor Jojo Shea, who was my PhD supervisor back in the 1980s. And his then graduate student, and this is in the late 90s when this came about, Sean Harrell. They were working on this problem the same way I was at the time. We discovered we were working on it independently. They were quite ahead of where I was, so I was able to incorporate a lot of their work and produce this presentation in order to give to the REU students at the RCU Observatory and now in this recording. So how many of you know how a refrigerator works? It's a fairly straightforward process where a gas is controlled through a compressor. It gets compressed. When you compress a gas, it heats. I use a radiator to remove that heat from the compressor, and then the radiator pumps that air out, or the compressor pumps that air out through an expansion process into what's called the evaporator. And in the evaporator, the air, because of the rapid expansion, is cooled, and then you use a fan to blow that cool air into the area, whether it's as an air conditioner cooling a room or a car or a refrigerator cooling your food. And then that compressor then pulls that cooled air back in, recompresses it, and completes the cycle. That's going to be really important in understanding how this non-intuitive thermal structure comes about. Let's start off by talking about atmospheric structure. We live in the troposphere, and the troposphere is a region where weather occurs. In the troposphere, the temperature decreases with height. If any of you've ever climbed a mountain, you're aware of that, or driven up a mountain. You know that it's colder at the top. It could be snowing at the top of the mountain and nice and warm on at the land around it below. Uh, and so that's simply thermodynamics. And until you get to the tropopause, and then at the tropopause, that cooling flattens out, and you start to heat into the stratosphere. And this heating in the stratosphere occurs because ozone absorbs solar ultraviolet light, and that ozone then heats and produces a structure where up to nearly 50 kilometers the atmosphere is heating. So around say 10, 15 kilometers up to about 50 kilometers the atmosphere is heating due to ozone. Now the ozone layer starts to peter out at the top of this point, and so it doesn't absorb enough solar radiation to heat anymore, and you fall into the mesosphere where the atmosphere is almost purely nitrogen and oxygen, and again you fall into this cooling uh, with altitude region until you reach around 90 kilometers, what's called the mesopause. Uh, and above that, you again have absorption of solar radiation, this time in the soft X-ray regime, which ionizes uh, atoms and molecules. And that ionization process reheats the atmosphere. You enter the thermosphere. Okay, and we're going to be talking about the mesopause, but we're going to also be talking about the mesosphere, stratosphere, and troposphere because they all play a role in this process. Okay, um, So, and a few other things in the troposphere, we have an unstable atmosphere which allows weather to occur. We have orography on the surface where winds can pass over and cause waves to propagate. And weather also causes waves to propagate up through the atmosphere, and that's going to be very important. Those are what we call gravity waves, not to be mistaken for gravitational waves. These are waves in which gravity provides the restoring force. When you enter the stratosphere, because of the heating, as you go up with altitude, air does not actually penetrate easily. So air pockets or balloons and the like have a very hard time lifting up through the stratosphere. It's because the heat, the warming air resists that, uh, and so. But waves can propagate through the stratosphere because they're not moving material upward, rather they're moving energy. Uh, And then in the mesosphere, as I mentioned, is a relatively inert to dynamically unstable region because the temperature is decreasing. So here's the problem. At the mesopause level, around 80 kilometers, mid 80s, more or less, the summer polar region is on average 70 to 80 degrees colder than the winter polar region. And this was measured back in the 60s and 70s by sounding rocket measurements, and later with measurements of air glow, and then much later into the 1990s using LIDARs. Uh, and this temperature distribution is far from radiative equilibrium and clearly must be dynamically maintained by adiabatic cooling and heating due to ascent and subsidence in the summer or winter hemisphere. And this is from a paper by Holton, 1982. So this is the structure of the atmosphere, how it would look. This is from a book, Andrews, Holton, and Levy from 1985. This is how the atmospheric temperature structure would look in January uh, if the atmosphere was completely radiatively determined, so no dynamics involved. And you see here we're in January, so the southern hemisphere is in summer. You have a nice stratosphere here. This goes up to about 80 kilometers altitude at the top. And so around between 40 and 50 kilometers, you have the stratopause, the highest temperature. Here you have the stratosphere, and then below, this plot doesn't take us down into the troposphere. But if you go to the winter side, you discover that there is no stratosphere. The temperatures have been decreasing throughout the troposphere, and they continue to fall right up into the mesosphere. Okay, but this is not what the temperature structure actually looks like. It looks a bit more like this, where you have the structure very similar to what you saw in the Levy et al. The Andrews et al. Graphic. This graphic goes up to 100 kilometers because I want to show the mesopause, and the mesopause, if the Andrews book had included it, you would have seen it here around between 80 and 90 kilometers. Okay, but on the winter side, you still do have a stratosphere. Okay, you do have heating in the stratosphere, and uh, and as a result, you also then have a mesopause. You can also see that the mesopause is higher in the winter side than in the summer pole. Okay, that's not something we'll discuss in detail in this presentation, but it's an interesting phenomenon as well. Okay, so what's the problem? The thermal structure of the stratosphere mesosphere is far from radiative equilibrium. Thus, mechanical forcing is required. There's pretty much no other way to to produce such amount of thermal structure change over the radiative form other than using some sort of mechanical forcing, a refrigerator. Okay. The complication is the following. If you think, well, okay, well, the summer pole, because the sun is on the pole all the time, you're going to have heating, makes sense in the lower atmosphere, and that heat is just going to propagate upward, and the atmosphere is going to expand, and in its expansion, cool, and so that will cause it to cool the summer side, and then because of that expansion has to then propagate uh, around the globe to the winter side, which is in darkness, and so that expanding air then subsides in the winter side, and there's your refrigerator. Now you're done. And unfortunately, that doesn't uh, provide sufficient forcing to induce the non-intuitive structure that we see, which raises the question: what drives the refrigeration process and how? Okay, so let's have some definitions here. First of all, radiative heating and cooling is basically temperature change by absorption or emission of radiation. You absorb radiation, you heat. You emit radiation, you cool. Just that simple. Atmospheric gravity waves, as I mentioned earlier, these are fluid fluctuations where gravity is the restoring force. Geostrophic winds, these are winds generated by differences in pressure. And Coriolis force can then come into play here as well, as you'll see in the presentation. The Coriolis force, or Coriolis effect, really, it's not really a force, is the deflection in the motion of an object that's moving in a rotating frame of reference. So if you're going around a merry-go-round in a park and you walk from the center out to the edge and somebody's looking from a stationary point of view off the merry-go-round, they see you actually moving not in a straight line towards the edge, but in a curved path, and that's the Coriolis effect. And as I mentioned earlier, a refrigerator, which is a system of dynamical cooling through expansion and compression. Okay, so let's start to talk about atmospheric circulation. This is going to be the first part of the explanation. There are two parts: circulation and waves. Atmospheric circulation is moderated by solar tides. Primarily. The sun heats the day side of the earth, causes expansion and movement of air, uh, and that then movement goes around the earth uh, and uh, and creates the movement. Also, you have the rotation of the earth. The rotation of the earth, of course, you have a gas surrounding a rotating sphere, so that gas is going to drag, so you get some wind as a result of that. You also get geostrophic winds that are caused by pressure gradients, and then later on we'll talk about atmospheric gravity waves. There are other phenomena as well. They're not so relevant for this presentation, although they do play a role. So let's start out by talking about solar tides and primarily geostrophic winds. So this is a graphic from a professor at the Eastern Illinois University who, unfortunately, I've forgotten his name, but he did give me permission to use this graphic, and the link to the original is below. And this shows what are called circulation cells. You have the Hadley cell, uh, that's in the tropical region. You have the Ferrel cell in the mid-latitudes and the polar cell in the polar regions. And these cells occur because of solar heating. This is where we talk about solar-induced tides. The equatorial region is quite warm, causes from having the tropical sun, causes the air to rise through the atmosphere until it reaches the tropopause where it can't rise anymore. And because you're at the center of the Earth, basically there's only one way to go, which is toward the poles in one direction or another. Let's just pick the northern hemisphere where we live, or at least where I live, just as to work with just one. So this air propagates toward poleward, and also descends with the reduction in altitude of the tropopause and also just and gravity. And eventually, around 30 degrees latitude, or what are called the horse latitudes, it then descends to the surface of the Earth. And so you get compression in this region. It's part of the reason that you have deserts at 30 degrees latitude because of this compression. Okay, and then it cycles back. Okay, and here you have what's called the Hadley cell. Now, this air that's moving, in this case southward or equatorward, is moving with a very slight increase in its radius and the distance from the rotational axis of the Earth, and then because of that, it's moving outward, and the Coriolis effect kicks in, and that's what gives us the trade winds. So this air moves downward towards the equator, or equatorward, better said, and because of the Coriolis force, gets dragged westward. So this produces easterly winds. Okay, the comparable cell at mid-latitudes, the Ferrel cell, because you have now subsidence occurring at 30 degrees. You have surface winds that are propagating poleward. And because these are propagating poleward with a component towards the axis of rotation of the Earth, you get westerlies. Okay, the Coriolis force will push this air in an eastward direction, or that is westerly winds, and then this peters out right around the edge of the polar region, and in the polar region again we have easterlies because of this. The circulation has reversed, and the prevailing surface winds are equatorward. Okay, so that's the start of that tropospheric circulation, and now let's move to the stratosphere. And in the stratosphere, we have a different situation because we have the summer pole, polar region. You have ozone absorbing sunlight, while in the winter pole, it's in the dark, and so you're not absorbing sunlight. So you have a warm stratosphere uh, in the summer pole, and that air wants to expand, and there's only one place to go, southward. And eventually that propagation ends up in the winter hemisphere, although these are separate, but the effect anyway is that you get uh, equatorward wind or airflow in the summer hemisphere, and the Coriolis force then will, as we saw with the surface winds in the tropics, push this flow westerly or westward, and therefore we have easterlies. So the winds coming from the east or easterlies towards the west. Whereas in the southern hemisphere, you have the opposite. You have westerlies. Okay, and this is going to be very important. So I want you to remember that you have summer easterlies and winter westerlies in the stratosphere. It's going to be very important later on in the presentation. And now we can go, now that we have the main circulation uh, laid out, we can start to talk about how this is modified by gravity waves produced by weather, wind over orography, the jet stream, the like. Okay, and gravity waves are atmospheric pressure waves that are produced by processes such as convection, for example, thunderstorms, winds passing over mountains, and the jet stream instabilities and the like. And their amplitude will increase as these waves propagate upward into thinner atmosphere, just like the tip of a whip uh, has much higher amplitude than the handle when you crack a whip, because you go out to a thinner and thinner leather. Well, as you go into thinner and thinner atmosphere, these waves will also expand and grow in their uh, in amplitude, and that's going to be important in terms of the effect on the mean winds. And these waves can carry large amounts of energy. Just think about a thunderstorm. Single thunderstorm can produce as much energy as is used by all of humanity during the same amount of time, or on that scale. And so there are large amounts of energy in thunderstorms, and that energy a lot of that energy is contained in its convection, in the upward movement of air, which then transfers energy to waves which travel upward into the atmosphere. Now, when the atmosphere gets too thin, when you get high enough, the waves will break, and when they break, they're going to affect wind flow. Okay, they also couple to wind, and you'll see that as well. Okay, and this graphic is from my former graduate student, his PhD thesis, Paul Kasselberg, just showing what I'm talking about here. You see convection from storms, wind over mountains, and then the jet instabilities that produce waves which propagate up through the atmosphere. They break in the upper atmosphere and produce all kinds of phenomena in the upper atmosphere and near space environment. And this is a video from Dave Fritz from GATS Incorporated in Boulder, Colorado. This shows the mixing of air. If you have, you start out with laminar flow with shear, eventually that produces turbulence, and then you start to see order coming together again, and that flow becomes more and more laminar, although always with a little bit of turbulence. And so I'll run this video again so you can see at the beginning. You'll see that and I should explain that this upper frame is looking down on the fluid. This frame is looking on the side, and this frame is looking end on. Okay, and as you'll see at the beginning, what you have are these layers, and the top will be a single layer, and then you'll have these nice flat layers, and the different colors are just the different flow directions. Okay, so that produces shear. So the flow is left and right, and then you'll see what happens as those flows start to interact with one another, create turbulence, and then again, as you see here at the end, creating a coherent structure. So again, you have nice laminar flow, and it starts to get turbulent as the layers interact with one another. Now you have lots of turbulence. Coherence is building and starting to now form the layers again, all with a little bit of turbulence, and it will keep cycling through that. Okay, so this is some of the things that happen when waves are traveling up traveling within a fluid, and this includes our atmosphere as a fluid. You can see that they're very dynamic. Okay, now here's another phenomenon, really very interesting. These are gravity waves that you see in air glow. So if I'm looking at these are actually not clouds, but they're air glow. These are emissions of light from OH molecules at around 80 kilometers. Okay, and we have near the ground, you're gonna see some thunderstorms occurring, and those thunderstorms are like dropping rocks in a pond and causing these, uh, causing ripples in the air glow. Okay, you also see stars, you'll see airplanes flying over now and then. But the main thing I want you to focus on is the uh, is the uh, are the gravity wave ripples in the air glow. Okay, because you can see the ripples. You can also see lightning strikes here. Sometimes you'll even see sprites, lightning going upward. Okay, and the ripples coming out. Okay, so again, gravity waves. These are gravity waves that are generated by deep convection from thunderstorms. Okay, you see some more sprites there towards the end of the video. Okay, so now let's try to bring these together: the mean circulation and the waves interacting. And there are two ways that waves can interact: coupling and breaking. Okay, so we'll start out talking about coupling. And here we have a video of, and hopefully it works, of surfers. Well, if you've ever surfed, you know that if you don't match the speed of the wave will go right out from under you, right? It'll just pass right under you. But if you match the speed of the wave, then you just stand on your board and the wave will carry you, okay? So what's happening here is you have coupling between the wave and the surfer, the surfboard, okay? And that allows the surfer to just ride the wave. They're just coupling together. Okay, that's going to be very important because the gravity waves, which carry tons of energy, coupled to the mean wind, they can then accelerate the mean wind. Okay. Now, wave breaking is a little bit more difficult, but suppose that you drop a rock in a river. The river's flowing. Okay, so the ripples come out, but the ripples then are getting moved by the river, and so you get this situation where you drop the rock and the waves are moving along with the flow of the river, and you kind of get the waves bunching together on the forward side, the movement direction, and then spreading on the back side. Now, if the river is going fast enough so that the uh, the waves in front really bunch up on top of one another, you form what's called a shock front, where the waves are all on top of one another. And this is what occurs, for example, in a sonic boom. When an airplane is traveling at or faster than the speed of sound, all the sound waves pile up at the front of the plane and form this shock front, and that makes a boom. Okay, and if you're going faster than the wave speed, then the shock front forms a V. Okay, and so that the uh, and that shock front basically is pushing. You have the pushing against the flow of the water, and uh, and so impeding the flow. And you can see that even a duck can travel faster than the wave speed on the surface of a pond. And you see that here's the shock front, okay, and you have the waves, the ripples behind, and then nothing in front, okay. And these waves can actually impede the flow, the mean flow of the fluid, okay, the river in this case, or the atmosphere. This is a case where you have an island uh, in the middle of the Pacific Ocean with 1,000 or more kilometers of basically flat ocean that the winds travel across before they get to this island. And when they get to the island, then you have this really nice laminar flow of wind that's suddenly pushed up by the island, this rock in the middle of the ocean, and that creates waves. Where you have compression, you have nice clear air, and when you have expansion, you get cooling, and you get condensation and clouds form. Okay, and again, you can see that there's a shock front formed, and uh, and this spreads out and can interact then with the mean wind flow. Okay, so here we go. Now we're going to couple these together. The graphic on the left shows the winter condition, and remember that remember that we have in the stratosphere winter westerlies. Very important. Okay. So gravity waves in the winter, turns out from measurements that they tend to have a slightly westerly flow or velocity, and but start with a pretty small velocity. And whereas the winds, which are also westerly, tend to be higher. And so if the now again, if the waves match speed with the wind, they'll just couple to the wind. But if the wave velocity stays low enough, so they stay below the wind, then they'll propagate through the troposphere, get past the tropopause and into the stratosphere, and at some point, because again they're expanding with altitude, you get the winds accelerating as they get into thinner air, and at some point they're going to match speeds with the mean wind, and when they match speeds with the mean wind, they couple, and then they join the mean wind flow at this altitude. Okay, and that's called wave filtering height. So the waves are filtered by the mean wind as soon as they match the speed. They couple there and they don't propagate further upward. Okay, so basically these winds act as a filtering mechanism, and any waves that can propagate and get through the lower parts of the atmosphere eventually get filtered in the upper atmosphere. Okay, and this accelerates the westerlies at the high altitudes. Okay, meanwhile in the summer, the waves actually propagate a little bit faster in summer than in winter, according to the sounding rocket results of going back into the 1960s. And you still have the tropospheric westerlies, but again, when you get to the stratosphere, now we get the summer stratospheric easterlies. They're caused by the equatorward propagating air mean flow. And now the waves and the winds are traveling in opposite directions, so that there's no filtering that happens. But when the waves get to the point where the difference in the velocity to the wave velocity and the mean flow matches the maximum wave velocity in the atmosphere, okay, hit the speed of sound, if you like, though that forms a shock front. And here we have the shock front, and what will happen at that point, when you have that shock front, the waves will break, that energy will get deposited into the mean flow, and that will actually break down the wind flow at that altitude. Okay, and that's now very, very important. We have wind breakdown in the upper mesosphere in the summer, and we have wind coupling, wind acceleration in the winter hemisphere. So now if you think about it, up in the upper mesosphere, the winds in the summer have stopped and the winds in the winter have accelerated. And now we can explain what happens and see if this animation will work. Well, this animation for some reason doesn't work, so I'm going to explain it. The blue patch are the gravity waves, and at the summer pole, where you have summer easterlies, okay, so the winds are propagating in a clockwise direction by looking at it, and the gravity waves propagate westerly, and they go in opposite directions, stop the wind, okay? And then on the winter side, it goes the opposite direction. I'll have to fix that, but I do have another animation, which is why I'm going to continue. In this case, the red dot in the summer is in the summer hemisphere. The green is the mean flow. The red are the gravity waves. Okay, and in the southern hemisphere, we have the green again. It's the mean flow. The blue then will be the outward flow from the pole. So basically, here's the mean flow. Okay, the winter easterly, the summer easterly, stops the gravity wave stops the mean flow, flows down, that air mass flows downward to the summer pole, accelerates the mean flow, and then because you're at the pole, there's no other place for that air to go except for down. It's like a toilet flushing or draining a bathtub. And so that what you have here is when you stop the mean flow, you push the air outward, you have expansion. You come down to the southern hemisphere, the southern pole, where you accelerate that flow down, and that goes downward like a drain and sucks downward, and that's compression. So the expansion region gets cooled, the compression region gets heated, and there is your refrigerator that cools the summer polar mesosphere and heats the winter polar mesosphere. So in conclusion, the summer mesopause at between 80 and 85 and 90 kilometers is the coldest place on Earth. Then the temperature structure in the upper mesosphere is inverted from the intuitive radiatively controlled form, which implies a dynamical heat transfer, therefore a mesospheric refrigerator. And the evaporator compressor cycle is driven by gravity waves, which on the summer side break down the geostrophic wind flow and enhance the meridional flow towards poleward, and that passes the pole and heads down towards the winter hemisphere, where gravity waves now have enhanced the zonal flow and therefore created a drain uh, dynamic, and that produces a pole-to-pole airflow that expands the air over the summer pole, compresses over the winter pole. You cool the summer pole and warm the winter pole, thus producing the structure as observed. And finally, some references of articles that you can look at to uh, learn more about this topic.